For my honors project, I created a program that could take in a sound wave signal from the microphone, process and analyze it, and let the user know if the frequency conforms to the intonation of the 12-note chromatic scale of Western music. It is similar to a software called Smart Music, but allows the user to play anything they want, rather than selecting a specific piece from a limited library. Here is a demonstration of the code when the person plays in tune. This is the output when someone is in tune. As you can see, most of the values in the in tune column are 0, and the deviation is usually less than 10 cents. And here's what happens when they are out of tune. What happens when most of my notes are sharp. As you can see, most of the deviation is very positive, and the in tune column is mostly 1s, which means I was very sharp. Finally, this is what happens when I play flat. This time, most of the in tune values are -1, which means I was very flat, and if you look at the deviation, the numbers are very negative. This project has 2 parts to it, the tuner and the analysis and organization of the feedback. I use 3 main functions for frequency analysis for the tuner. The closest note function takes a frequency and finds the closest letter note to it. Here's what the function outputs if I input a frequency of 441 Hz. As you can see, it is closest to an A4, which is 440 Hz. The calculate sense function calculates the difference in sense between the input pitch and the expected pitch. Again, with an input of 441 Hz, let's compare it to the actual pitch, which is 440 Hz, and see what the difference in sense is. In this case, the difference is 3.9 cents. Finally, the in tune function determines if a note is flat, sharp, or in tune based on a tolerance of 10 cents. The in tune function outputs a -1 if the note is flat, a 0 if it's in tune, and 1 if it's sharp. So with a 441 Hz input, we can see that it's in tune since the difference is only 3 cents. I then define a callback function that is called every time new data is available from the microphone. The function takes the incoming data, applies a fast Fourier transform to get the frequency spectrum, and finds the maximum frequency. It then uses the closest note function to find the closest letter note to the frequency, and the in tune function to determine if the note is flat, sharp, or in tune. Finally, the function outputs the closest note and the difference in frequency in cents. The fast Fourier transform is used to transform an analog wave sound to a digital signal, which can be further broken down into its constituent frequencies. This is done by taking a window of the digital signal and performing a mathematical operation on it called the discrete Fourier transform. The fast Fourier transform is used in this program because it is more efficient than the DFT, since it splits the signal into smaller sections and performs DFT on those sections rather than doing DFT on the entire signal. After FFT is applied, the frequency domain representation can be visualized using a spectrum analyzer, which can be used to identify the frequencies present in the incoming sound wave. I think this was the most interesting piece of information that I had to learn about to continue with this project. After this, we create a pandas data frame to store the recorded and actual frequencies, which can be analyzed by the user to better understand their performance. A sound stream is set up using Sound Device to start listening to the microphone. When the program is interrupted, the sound stream is stopped, and the feedback information is stored into a data frame for the user to view and use for their own improvement, with feedback information like the recorded frequency, the note played, the in-tune frequency, the deviation from the actual note in sense, and whether it is considered in tune or not. While the most basic features of this program are functioning, there are a few improvements that can be made to make it an even better design, such as detecting when there is a note change rather than sampling frequencies at a constant rate, adding a visual representation of the data, and allowing the user to adjust the sensitivity and how much deviation is allowed to be considered in tune.